Life on Earth was made in rivers. Perhaps not born, but made. Before our ancestors evolved the strength to swim against them, oceanic currents, rivers within water, carried their feeble forms across the planet, dredging from the depths the nutrients on which they fed. When life began its painful rebirth onto land, it was by rivers that the first plants congregated, the first soil formed, and in which the first pioneers lived, mated, and died. Rivers fed the watering holes around which animals socialized with, challenged, and preyed on each other, and, once our ancestors had mastered farming, the locus for what would become civilization. We used to believe that our world was unique in possessing rivers, but we now see them across the solar system. Great glaciers, rivers of ice, have been seen on Pluto. Evaporating streams have erupted from the soil of Mars, and of course, rivers of liquid methane are now known to flow across the surface of Saturn's moon Titan. Even the rings of Saturn, composed of solid particles of ice, ebb and flow as chaotically and fluidly as a liquid. Outer space, the dominant environment of the universe, will not allow liquids to form. Of the residual speck of matter not superheated into plasma or invisible to any of our detectors, only two states persist: solid or gas. So the raging mass of particles around Saturn may represent the closest to a river much of the universe ever sees. Many such rivers exist within our solar system, of course, though they are mere denuded rivulets compared to that around Saturn. The rings of Neptune and Uranus are composed of broken, blackened lumps trailed by dust. They are captured icy irregular moons, the remnants of comets or asteroids fractured by their immense gravity, careen around their captor in wild orbits, often until they collide with one another or fall into the planet's atmospheres. But the solar system's greatest river is so vast it is yet to be fully mapped, and only in the last few decades have we even begun to grasp its true extent. It spans the solar system entire, to the outermost reaches of the sun's gravitational pull, and nearly as far as the closest stars. This river, if you can call it that, is so tenuous that an average human is unlikely to see more than a scattering of its isolated particles, which we call comets, in a lifetime. Yet, said particles comprise the majority of the solar system's water. For millennia, the components of this river were thought to be random interlopers into the settled order of nature. But we now know that, far from random, these icy visitors follow invisible courses defined by the gravity of the planets. They pass through narrow clefts like waterfalls, collect in orbiting populations like swirling eddies, before being sent into the sun, or outward to the solar wilds to repeat their journey again. An ebb and flow that takes millions, even billions of years to complete. Speculation on this river's full extent began as far back as Edmund Halley, who was the first to realize that comets followed predictable, calculatable paths. But its true form and scope were not wholly envisioned until the mid-20th century, and would require the discovery of another, far grander river. The man who found both was named Jan Hendrik Oort. Jan Oort was born in 1900 in the Netherlands, a country which, since giving the world the telescope, has gone on to produce a parade of accomplished astronomers, one of whom was Oort's mentor and advisor, and I hope I'm pronouncing this correctly, Jacobus Kapteyn. Kapteyn's passion, throughout his working life, was understanding the motions of stars, a passion which led to his discovery of what is now named Kapteyn's star, a nearby red dwarf rocketing through the sky at 243 kilometers per second, making it one of the fastest stars known, and in the opposite direction to other, more familiar stars. While the discovery fascinated Kapteyn, he failed to grasp its full implications. Kapteyn subscribed to the then widespread belief that the Sun occupied a privileged central position in the Milky Way galaxy, a belief validated, Kapteyn assumed, by his own observations, particularly his measurement of the star's motions. This was not the monumental act of collective egotism it appears from our own time. Until Edwin Hubble's work in the 1920s, it wasn't even clear if the so-called spiral nebulae were outside our own galaxy, let alone how far away or large they were. Even those who subscribed to the notion that they were island universes outside our galaxy assumed that they, and by extension the Milky Way, were far closer, and thus far smaller, than we now know them to be. Hubble would deliver the first blow to Kaptein's universe. Jan Oort would collapse it. Although from a scientific background, his father was a psychologist who ran a mental institution, Jan Oort did not turn to astronomy until he encountered Kaptein. It was largely due to Kaptein's encouragement that Oort took up astronomy, and not a coincidence that his first work involved tracking the motions of stars. But Oort would not follow the way of his master. Following on from the work of a Swedish astronomer named Bertil Lindblad, Oort realized that the mass of the galaxy had to be concentrated toward the center, and that the stars followed a set series of motions, now called Oort's constants. What Oort's constants revealed, essentially, was that the farther away a star was from the galactic center, the more slowly it moved. This revealed to Oort that the entire galaxy, like the rings of Saturn, must be rotating around a central axis in one great arcing wave. In 1951, Oort published a paper that showed that, far from privileged, our Sun was a full 28,000 light-years from the galactic center, just one particle in the vast seething ocean of stars. Kaptein's earlier observations suggesting the Sun's centrality were handicapped by the dust which obscured much of the Milky Way from view. With the rise of radio astronomy, a discipline Oort himself did much to launch and promote, particularly in his native country, the dust could be penetrated, and the galaxy's true magnitude could be grasped. While the galaxy was Oort's living, it was not his passion. Oort only found his passion when, sometime in the 1940s, he advised a graduate student named Adriaan van Werkholm, whose work had already disproven many of the previous hypotheses for the origins of long-period comets, i.e. those with thousand-year orbits. Comets soon became Oort's hobby, and in 1950 he realized that they were tied to his discoveries on the motions of stars. Given their volatile composition and close passes to the Sun, every long-period comet should have disappeared billions of years ago. For them to still exist today, there must exist some outer reservoir from which they were continuously harvested. Oort realized that this reservoir could not be interstellar space, since if it were, then we would see a far larger percentage of hyperbolic comets, that is, comets with open-ended orbits, than we do. We may conclude, said Oort in his paper, that a sensible fraction of the long-period comets must have come from a region of space extending from a distance 2a equals 20,000 to a distance at least 150,000 AU from the Sun, that is, almost to the nearest star. That does not mean that they are interstellar. They belong very definitely to the solar system, because they share accurately the Sun's motion. Because long-period comets were isotropically distributed, in other words, they arrive from every point in the sky equally, the region of space must be not a circular belt, but, quote, a huge cloud, extending according to the numbers cited above to distances of at least 150,000 AU and possibly still further. Oort's cloud was the wall encasing our solar system, its final structure, marking the outer boundary of the Sun's gravitational dominance. Oort estimated that the cloud must comprise at least 100 million individual comets, totaling a tenth of an Earth mass. Today, astronomers believe Oort's values were too conservative. Modern estimates suggest the cloud contains trillions of objects at least 1 kilometer in diameter, totaling as much as 5 Earth masses. The question remained, however, precisely how the particles of this cloud ultimately livened the skies of the inner solar system. For Oort, there could only be one mechanism: the gravity of passing stars. The flowing river of the galaxy was the source from which the Cometary river flowed. The actions of passing stars meant the cloud could not extend farther than 200,000 AU. Conversely, because no star had passed closer to the Sun than 20,000 AU, it would be unlikely to see a long-period comet with a point of origin closer than that, a hypothesis that fit well with observations. Today, not only do we accept that the gravity of passing stars plays a key role in sending Oort cloud comets inward, but that they may do so on a scale Oort never contemplated. Oort said that no star has ever passed closer than 20,000 AU from the Sun. Thanks to data from the Gaia astrometric probe, we now know that not to be the case. Calculations show that in about 1.4 million years, the small star Gliese 710 will pass as close as 13,000 AU from the Sun, potentially interacting with the outer comet cloud, and turning a steady trickle of comets into a raging torrent, vastly increasing the possibility of a collision with the inner planets. Halfway through his paper, Oort hit the brakes to say that he just received word from Fred Whipple, of Dirty Snowball fame, that a similar idea had been proposed 18 years earlier by an Estonian astronomer named Ernst Öpik, though Öpik never went as far as to envision a cloud. For Öpik, the perturbations of stars would limit the orbits of comets to a mere 2,000 AU, a hundredth what Oort's calculations had revealed. Incidentally, Ernst Öpik's grandson is British politician Lembit Öpik, former president of the Liberal Democrat Party and current parliamentary chairman of the Space Kingdom of Asgardia. I wish I was making that up. In his paper, Oort concluded that the residents of the cloud could not possibly have formed where they were. There, in the wilds of interstellar space, matter was too thinly spread to come together in such quantities as to form a comet. Rather, the objects that comprised what in less than 2 decades from his paper's publication would be called the Oort cloud had to have formed farther in and have been cast to their current orbits by the gravity of the giant planets. To Oort, the only difference between a comet and an asteroid was that a comet was far enough from the Sun not to be baked by solar radiation. The comets of the Oort cloud had formed in the same spinning disk as the planets and the asteroids, only beyond the so-called frost line where ice and rock could mix equally. Those asteroids with orbits elongated enough to be caught by the giant planets were then cast into the outer reaches of the solar system, lifted further by the gravity of passing stars, and formed the Oort cloud. This model, broadly speaking, has remained largely unchanged in the 70 years since Oort proposed it. Indeed, comets with orbits suggesting an origin in the Oort cloud have been found to comprise material similar to rocky asteroids, which therefore would have formed much closer to the Sun. Computer models have suggested the Oort cloud reached its maximum mass only 800 million years after the solar system's formation, when the Earth was only just showing the first signs of life. Over the following 4 billion years, that mass has been gradually, inexorably depleted. In the last 10 years, however, questions have been raised about Oort's domestic model for his cloud's formation. More complex computer models, such as that proposed by Hal Levison in 2010, have suggested it may only account for about 6 billion of the trillion comets in the cloud. That they could have been captured from interstellar space in the age of the solar system is essentially impossible. Instead, it seems the vast majority of Oort cloud comets were swiped by our solar system from the stars that shared its birth cluster. This means that Oort cloud comets potentially carry the chemical signatures of other stars. There is another force in the distant solar system that Oort did not account for: the tide. And for once, I'm not being metaphorical. From our limited human perspective, we tend to see the tide as purely a property of the sea. But it is, without exception, an astronomical phenomenon. As children, we are all taught that tides are caused by the gravity of the moon, but we seldom grasp the full implications of that fact. Tidal forces are exerted whenever 2 large bodies come into close contact with one another. Gravity's effect reduces with distance, which means that objects in close proximity experience a gravitational gradient. At the tip of their facing side, the gravity is substantially stronger than at their core. This difference in gravitational strength causes each body to descend laterally, squashed like a rugby ball. On Earth, this takes the form of the ocean bulging upward twice a day, while the moon experiences tidal earthquakes, or moonquakes, lasting over an hour. Jupiter raises tides on its moon Io strong enough to almost tear it apart, while similar, if weaker effects may just grant Io's sister moon Europa an internal liquid ocean. Tidal force pulls galaxies into sinuous tails and loops, and rips objects approaching black holes into their component atoms. And as our sun plods its way on its 225 million year journey around the galaxy, it feels, ever so slightly, the collective pull of the galaxy's tidal force. For our species, huddled as it is within our sun's vast gravity well, the galactic tide may as well not exist. But at the distance of the Oort cloud, and across its vast extent, the tidal gradient of the Milky Way's collective gravity becomes relevant. If a comet within the cloud has an inclination sufficiently high relative to the galactic plane, the galactic tide distends its orbital path, making it more elliptical, pushing its perihelion forward until it comes into the path of Neptune. Neptune then either flings the comet outward, whereupon it falls back into the Oort cloud or continues into interstellar space, or sends it inward, where it falls under the influence of the giant planets, Jupiter and Saturn. The gravity of passing stars will then reshuffle the Oort cloud, sending more comets into the high-inclination danger zone. Astronomers estimate that up to 90% of long-period comets that enter the inner solar system are brought by the galactic tide. What the dislodged object passes as it crosses the untold trillions of miles between the Oort cloud and the charted regions of our solar system, no one can say. The vast majority of our solar system, over 99%, is unknown. But eventually, after tens or hundreds of thousands of years, it falls within the gravitational range of the four gas giants, which together act as the engine powering the flow of objects between the farthest and innermost reaches of the solar system. While comets do indeed collide with planets, as Jupiter has frequently shown, a more likely result of such an interaction is for the planet to slingshot the comet into another orbit. Once it crosses into what might somewhat melodramatically be called known space, a comet has a strong possibility of encountering Jupiter or Saturn and being sent into interstellar space. The Jupiter barrier is the reason the number of Oort cloud comets is 10 times higher on the outer solar system than the inner solar system. If, however, the galactic tide has decreased the comet's perihelion to less than 3 astronomical units, then it has a chance of being sent into the inner solar system and becoming what stargazers call a new comet. One thing Oort's model could not resolve is why so many long-period comets, roughly 30%, are new instead of returning. One possible answer is the idea of cometary fading. A comet may return many times, but only be visible for a sparse few returns, after which it exhausts its supply of volatile materials to form the tail that renders it visible to our eyes. Of course, if its orbit is sufficiently open-ended, or more technically, hyperbolic, it may simply fly off into interstellar space anyway, once it slingshots around the sun. Or it may meet the eventual doom of all comets, and fragment. In 371 BC, a bright comet was observed by Aristotle, and is now believed to be the progenitor of multiple great comets, including those of 1843 and 1882, Comet Ikaia-Secchi in 1965, and Comet Lovejoy in 2011. Most notably, however, the comet is believed to have birthed the family known as the Kreutz sungrazers. A sungrazer is, as its name suggests, a comet that comes particularly close to the sun, usually within 12 solar radii. Often this is close enough to vaporize the comet, but if it's large enough, the comet can survive several revolutions until it finally dies. The Kreutz sungrazers are a family of comets whose farthest distances from the Sun all lie at roughly 5 times the distance of Pluto. Since arriving at the L1 gravitational point between Earth and the Sun, the Solar and Heliospheric Observatory, or SOHO, has incidentally discovered up to 4,000 smaller members of this family. If a long-period comet makes enough revolutions around the Sun, it may be caught by the gravity of Neptune or Uranus and have its orbit yanked downward, becoming shorter with each pass. Many of the comets that we remember, with orbits lasting only a few thousand years, are those the planets have managed to lasso in this way. Very occasionally, it may be yanked so hard, or so often, that it falls below the arbitrary 200-year dividing line and becomes what we call a short-period comet. Models suggest that this process can also happen in reverse, with Jupiter sending comets out toward Neptune, and Neptune casting them out into the Oort cloud. There is no reason to assume that the same object cannot be scattered in both directions multiple times, the ebb and flow lasting millions of years. Short-period comets originating in the Oort cloud are called Halley-type comets for reasons that I am sure are fairly obvious. Halley-type comets, though oddly not Halley itself, tend to have prograde orbits. They orbit the Sun in the same direction as the planets. This has led some to speculate that the Oort cloud may have an inner region, sometimes called the Hills cloud, that more closely resembles a flattened disk, as it is more strongly affected by the Sun's gravity. Incidentally, the reason a 200-year return time is considered the defining characteristic of a short-period comet is simply that the first predicted return of Comet Halley, and the first predicted return of any comet ever, occurred in 1758, or about 200 years before the terminology was first defined. Thus, any comet's orbits that fall after that point are likely to have already been recorded and calculated. If past records show a returning comet to have appeared in our skies at some point in the past 200 years, the IAU officially labels it as a short-period comet. And speaking of arbitrary terminology, you may have noticed that I've been somewhat mealy-mouthed in my use of the word comet, occasionally employing the word object. There's a reason for this, and not one I'm particularly fond of. Of the myriad objects sent into the planetary region by Neptune, only a fraction are officially referred to as comets. The others are referred to as asteroids, or, more diplomatically, centaurs. A centaur, officially, is any small object in the solar system outside the gravitational influence of Jupiter, but inside the orbit of Neptune. The definition says nothing about what the object is made of. To be officially classed as a comet, an object must pass sufficiently close to the Sun to produce a coma, or a cloud of material erupting from the surface. An object is classed according to its current orbit, regardless of how long it may remain in that orbit. In one sense, this is understandable, since without a space probe it is impossible to determine if an object is mostly ice, like a comet, or a rock with an icy coating. On the other hand, it leads to preposterous situations like centaurs being simultaneously classed as comets and as asteroids. Well, they are called centaurs, after all. There is another group of comets I haven't mentioned yet. Until recently, they've been mainly the interest of astronomers because, despite comprising fully 27% of all comets, and being relatively close to Earth, having orbits between 5 and 20 AU from the Sun, and despite having relatively low inclinations that keep them near the ecliptic, where the planets are, they're only occasionally visible to the naked eye. These comets are known as the Jupiter family, because they all appear to have been corralled into their current orbits by Jupiter, whose 12-year orbit lies within their region. They were completely disconnected from the Halley-type comets. No Halley-type has an orbital period of less than 20 years. No Jupiter family comet has an orbit higher than 20 years. In our increasingly strained analogy, they would be rivers without a common source, which meant, given that the Jupiter family comets had dynamical lifetimes of just 300,000 years, that there had to be two sources of comets in the solar system. Models developed in the 1980s suggested that the second source would be a belt, rather than a cloud, and roughly encase the orbit of Pluto, making it 1,000 times closer to the Sun than the Oort cloud. For many decades, the source remained a mystery, and then, in 1992, the headwaters, in the form of a tiny icy object near Pluto's orbit, then called 1992 QB1 and now called Albion, appeared over the horizon. Over the next decade, thousands of icy objects were found in similar orbits, many approaching the size of Pluto, which of course, in 2006, led to a quiet reclassification that to date has seen not a peep of protest. Unlike the Oort cloud, the Kuiper belt, as it is now laudably if inaccurately known, is, as its name suggests, a belt of objects, much like the asteroid belt, if the asteroid belt was made of ice and 20 times wider. Unlike the asteroid belt, which houses only one planet-sized object, the Kuiper belt, depending on how you define it, holds up to 7. And defining it has proven difficult. Astronomers seem permanently divided about what the Kuiper belt actually is, and where it begins or ends, sometimes even defining it differently in the same publication. So what makes a swirling mass of ice balls so darn complicated? Well, it turns out it's had a pretty heavy history. Planets don't move much these days. Well, I mean, they do, just not in ways you wouldn't expect. It takes a lot, and I mean a lot, to nudge a planet into a new orbit. Whatever chaos the planets may have endured in their distant past, they are over it now. The precise location of a planet, to the centimeter, can be calculated as far as 230 million years in advance. That is not the case with comets. Comets are playthings to planets, tossed between them at random. What's more, their orbits can be shifted by the pressure of the solar wind, or even simply sunlight evaporating one side more than the other. A comet's orbit cannot be accurately calculated even for a few dozen apparitions, which means we have no realistic way of accurately determining where it started from. We can only make educated guesses with computer models. Even the Centaurs, which are far more stable than comets, are not expected to last in their current orbits for more than 9 million years, with individual Centaurs lasting about 1 million years on average. Comets are far more easily affected by the gravity of planets, the sun, and passing stars. Computer simulations show that even altering a comet's initial position by 1 centimeter can lead to a vastly different orbital outcome. Which means, much like blood spatter or fingerprint dust, the pattern left by the objects in the Kuiper belt can reveal much about past events. And when it comes to our solar system, the past appears to have been very eventful indeed. Perhaps the most obvious archaeological element of the Kuiper belt is its tiny mass, less than 1/10 that of the Earth, and too small for it to possess so many dwarf planets. For its dwarf planets to form, the Kuiper belt must have originally contained 100 times as much material as it does now. It is similar to seeing an ancient building reduced only to rubble. If all you see is rubble, you might assume the ruin to have been a small house. But if among the rubble you spy a column, doorway, or buttress, you know that whatever stood there must have been a monumental scale. The Kuiper belt is divided into a number of regions. The main part of the belt, known as the classical belt, comprises the majority of Kuiper belt objects. The classical belt is further subdivided into the hot classical belt and the cold classical belt. These terms have nothing to do with temperature, but are references to the behavior of particles in a gas, which rise up when heated. The term derives from the fact that the hot classical belt has a far higher inclination, ranging up to 30 degrees, compared to just 5 degrees for the cold. But if that were the only difference, I wouldn't be talking about it. The hot classicals comprise 65% of the mass of the classical belt, and contain all of its largest objects, including every one of its dwarf planet candidates. The cold classicals top out at just 400 kilometers in diameter, less than 1/3 the diameter of the largest hot classicals. Also, they are different colors. Spectra show that cold classicals are stained deep red by eons of tholins, a carbon-based goop derived from the action of sunlight and cosmic rays on frozen methane that cakes the surfaces of outer solar system objects in much the same way that sand or clay cake the surfaces of inner solar system objects. The cold classicals also show evidence of pristine volatiles like methanol. Given that the Kuiper belt was initially believed to be an unspoiled fossil of the ancient solar system, astronomers expected all KBOs to be deep red, with the ages of tholin deposit unaffected by impacts or solar radiation. Instead, the hot classicals are neutral gray, and too homogeneous for their color to be due to impacts. Rather, it appears they originated from a region too warm for them to retain methane on their surfaces. The fact that they comprise so many large objects also suggests they form closer to the Sun, where the matter density was higher and dwarf planets could form. The second population, or rather populations, are the safe resonances. An orbital resonance occurs when two bodies lock into orbits that are precise ratios of each other, such as 3:1 or 5:2. If one of these bodies is substantially smaller, a resonance typically spells doom, because the larger object catches it at just the right moment to propel it out of its orbit and into interplanetary space, where it will either be caught by Jupiter and sent into interstellar space, or collide with a planet or the Sun. For this reason, classical belt contains a number of gaps, similar to the Kirkwood gaps in the asteroid belt mentioned in my video on the rings of Saturn, located at precise ratios of the orbit of Neptune, the planet that more than any other has shaped the Kuiper belt. But there exists a second type of resonance that, conversely, can actually protect an object from ejection. If the ratio is such that the smaller object's orbit always places it half an orbit away from the larger object, such as 2 to 1, 1 to a half, or 3 to 2, 1 to 1.5, then the larger object, Neptune in this case, will always be on the other side of the solar system whenever the smaller object completes its orbit. By far the most populated safe resonance is the 3 to 2 ratio, which comprises up to 15% of the Kuiper belt's entire population. Like the hot classicals, the resonance of the 3-2 resonance vary widely in inclination by up to 30 degrees, and also possess a number of dwarf planet-sized objects. Unlike the hot classicals, though, they tend to vary in color from gray to red, and possess more elongated orbits on average. In honor of their most celebrated member, the occupants of the 3-2 resonance are known as Plutinos. The final region of the Kuiper belt, as well as the most controversial and dynamically important, is the scattered disk, or, for pedants, the scattering disk. The scattered disk is the part of the Kuiper belt from which the Jupiter family comets actually derive, though it isn't so much a region as an orbital quirk. All scattered objects have perihelia, or closest distances to the Sun, within the gravitational range of Neptune, between 33 and 40 AU, allowing the planet to occasionally catch and throw them out of orbit, whereupon they are either scattered outward toward the Oort cloud or, less likely, inward, where, aided by a slingshot from Jupiter or Saturn, they descend into the inner solar system, with about 1/3 of them becoming Jupiter family comets. There is seemingly no limit to how far a scattered object's orbit can extend. The farthest known to date has an aphelion, or farthest point in its orbit, of 469 astronomical units, 12 times the distance to Pluto. These outermost objects comprise the majority of future comets. The innermost inhabitants of the scattered disk appear to be fossilized, with their orbits unchanged in the age of the solar system. Models suggest that Neptune scatters more objects outward beyond its orbit than inward, even perhaps to the Oort cloud, making the scattering disk a tributary of the Great River. In 2006, Hal Levison even speculated that the relatively low inclinations of Halley-type comets might be explained if they were originally scattered disk objects that went to the Oort cloud and back. The contributions of the classical belt and the resonances to the scattered disk is believed to be fairly minimal, both because the orbits of the classicals and resonances are relatively stable over the age of the solar system, and because the scattered disk has roughly the same population as the classical belt. If the classical belt were the main source of scattered disk objects, then the scattered disk would be far less populated than the classical belt. Very occasionally, however, via an impact or a rare quirk of orbital mechanics, a classical or resonant object can fall into an unstable resonance, whereupon it may end up in the scattered disk. And it is that fact that has made defining the Kuiper belt such a headache. Some astronomers argue that, since only a small fraction of the classical belt is able to enter the scattered disk, with most of it stable over the age of the solar system, they should be considered separate regions, with the Kuiper belt comprising only the classicals and the resonances. Others argue that, since the objects in the classical belt can and do become part of the scattered disk, the two are linked and should be considered equal parts of the Kuiper belt. The debate is ongoing and, like many controversies about the outer solar system, likely to remain so for the foreseeable future. Some astronomers have attempted to ditch the argument altogether and simply call the belt the trans-Neptunian region, a term that will become problematic should Planet 9 ever be discovered. So what happened? What created this multi-car pile-up at the fringes of deep space? Here, without the comfort of easy prediction, only computer models can help, and they may recently have begun to offer a solution. We know that the original disk out of which the solar system formed must have been relatively flat, since high inclinations create high relative velocities which in turn cause objects to shatter when they collide, rather than accrete into larger objects. For the same reason, we know that its comprising objects must have been in very circular orbits. For the Kuiper belt to have formed in the first place, it would need to have been both of these things, but today it is neither. We also know, as noted above, that the Kuiper belt must have contained a vastly greater amount of material, up to 100 times more, for objects as large as Pluto to form. Collisions could not have reduced such a mass of material in the age of the solar system, therefore it must have been ejected somehow. We know that several Kuiper belt populations, such as the Plutinos and the hot classicals, are a very different composition to the other members of the belt, and likely arrived there from deeper within the solar system. In attempting to unravel the mysteries of the Kuiper Belt and beyond, one is left with only one viable suspect: Neptune. Neptune is easily 100 times the mass of the entire trans-Neptunian region, that we know of at least, and its gravity alone shapes and molds the belt in its current form. Several models have been proposed over the years to explain Neptune's role in shaping the Kuiper Belt, all of which involve the planet migrating outward early in the solar system's history. The precise mechanism varies from model to model. Some see it as gradual, the result of minute kicks from comets. Others see it as rapid and drastic, the result of a billiards-like tumult among the gas giants. The most radical, yet arguably also the most widely accepted, is the Nice model, named after Nice, France, where it was formulated in 2005. Since I've already discussed the Nice model in detail in my video on Planet 9, I won't do so here. Regardless of the precise mechanism and mode of Neptune's migration, the effects are, by definition, the same. Neptune and the Kuiper Belt are believed to have begun their dance far closer to the Sun, with the edge of the far denser Kuiper Belt lying where Neptune is today. Neptune's orbit during migration would have been far more elongated than it is now, similar to that of Eris. This caused its resonances to overlap, and as those resonances advanced forward like a snowplow, they sent the KBO's orbits haywire. As Neptune interacted with the collective gravity of the Kuiper Belt, its orbit dampened and became more circular. The scattered objects, driven outward by up to 5 AU, were eventually trapped both into new resonances and into the hot classical population, their wild inclinations relics of their past trauma. But there was a problem. How could such a bulldozing have left the cold classicals seemingly unaffected? In 2018, Mike Brown and Konstantin Batygin proposed that if Neptune's precession, the orbit of its orbit, was particularly fast during its migration period, it could preserve a cold classical belt. So, once an object leaves this region, what happens to it then? The Centaurs are a fairly motley bunch. Some, like the cold classicals, are ancient red, while others are matte gray. Overall, the Centaurs have about 10 times the mass of the asteroid belt, with about 10 million objects larger than 2 kilometers and about 100 objects larger than 100 kilometers. The largest Centaur known is 10199 Caraclo, which is about 250 kilometers across. In 2014, Caraclo was found to have 2 rings in orbit around it, nicknamed Oyapoke and Kui, fittingly after rivers. Only about 6% of Centaurs actually become Jupiter family comets, mostly due to Jupiter throwing them out. In order to join the Jupiter family, a Centaur must pass through a very narrow cleft, known as the Gateway. Only discovered in 2019, the Gateway is a nearly circular orbit immediately behind Jupiter that is currently only occupied by 3 objects. Because it is such a transitory region, very few objects occupy at any one time, but it is believed that sooner or later, all Centaurs destined to become Jupiter family comets must pass through it. If a Centaur does not collide with a planet or become a Jupiter family comet, there is one other possible destination: accidental moonhood. The satellites of the outer planets, Jupiter, Saturn, Uranus, and Neptune, are divided into 2 main groups: regular satellites, which are moons that orbit their primaries in decent, respectable, planet-like fashion, and irregular satellites, which orbit their planet every which way. Leaving aside Neptune's moon Triton, which is very much its own thing and already covered in depth earlier in this series, irregular satellites are small, broken, pitted things, often orbiting their planet in swarms left over from being shattered, either by collisions with other satellites or through the planet's tidal force. A 2019 study of the carbon and hydrogen isotope ratios in the moons and rings of Saturn suggests that, somewhat surprisingly, they were very similar to those of Earth, except for Phoebe, by far the largest of Saturn's irregular satellites, whose hydrogen to deuterium ratio was 8 times higher than Earth's. While this might suggest, as it has on Mars and Venus, that Phoebe was once much hotter than the other satellites of Saturn, its carbon isotope ratio suggests that it never got hot enough for ordinary water to evaporate from its surface, indicating that it must have originated in a very different part of the solar system, likely the Kuiper Belt. The satellites of the outer planets share compositions with Kuiper belt objects and centaurs: water ice, ammonia, methane, and sulfur dioxide. However, they are not as red as Kuiper belt objects, likely due to collisions blasting their surfaces free of tholins. Phoebe is riddled with craters. Its composition is broadly similar to that of comets: water, carbon dioxide, and iron-rich silicates, though the water ice appears most prominent in the deepest craters. This suggests that Phoebe's surface was originally water-poor, but that water was brought up from the core by impacts. The regions around gas giants are the most collision-heavy environments in the solar system, so it would be misleading to directly compare captured satellites to the Centaurs. So, I hope I've given a brief overview of every reservoir of the solar system's icy objects. But there's one that I have not yet covered, that was only recently proven: interstellar space. That interstellar space may be an origin for comets have been speculated since comets were first known to be freely moving objects. But it wasn't until 2017 that the first object indisputably of interstellar origin was found. Oumuamua caused a kerfuffle when discovered, given that it appeared to resemble nothing in our solar system, but it was almost immediately joined by another, far more boring interstellar comet, Borisov. And that's not all. In April 2020, a paper published in the Royal Astronomical Society journal suggested that by analyzing the orbits of high-inclination centaurs, the centaurs may be home to 19 interstellar visitors hiding in plain sight. Calculations suggest that our Homey cubic parsec of space may contain more interstellar comets than those tied to the Oort cloud. We may have only begun to discover our solar system's greatest river. Well, that was the hardest video I've ever done. I knew I'd have to make it one day, and I was stewing in my head for months about how I could possibly make it interesting. So, apologies for how long it finally took. Longtime fans may have noticed that it covered material already mentioned in my video on Planet 9, but while some crossover was inevitable, I hope I managed to give a more in-depth explanation than previously. By my count, there are 4 more episodes left in this series, though my count has been wrong before, so don't take that as gospel. On a more fun note, my annual Halloween episode is coming up, and as per usual, it was going to be about nasty aliens or human extinction. But while I was making this video, it seems we may have found life in the earthly incarnation of hell. So yeah, I guess we're going there. Hopefully before October 31st. See you then!